And I'm going to walk through one of the topics in A-level mathematics, and this is differentiation, but in particular I'm going to deal with the differentiation. I'm going to deal with differentiation but of the sine and then the cosine. So this is what we are going to look at: differentiation of the cosine and the sine. So this is what we are going to discuss throughout this part, and we need to get to know. Differentiation is quite a wider topic, but we're going to see how do we basically deal with the cosine and then the sine as well. Now we deal with these things here using two methods. We are going to first apply using the first principles, and we shall also use what you call the chain rule. We'll try to use the chain rule, and we shall also use the first principles. Now, starting with the first principles, we all know that when we are differentiating from first principles, we know that dy dx from first principles, if you're differentiating, is the same as the limit as the change, okay, as a small change. The small change in x tends to 0, okay, small change in y out of the small change in x. This is what we know from first principles. Okay, so we are going to do a substitution here, and then we generate our derivative for the sine and then the cosine. Let's begin with the sine. Take an example. If we have a function y equals to the sine x, and we are told to differentiate this. So what do we do when we are dealing with the first principles? We know that dy dx, we do a substitution, will be the limit as a small change in x tends to 0. Okay, now our small change in y will be the sine of x plus the small change in x, okay, minus the sine of x. All this we divide through by the small change in x. That's what we do have. Now we need to generate this, we need to simplify this, but we go back to our rules, that's the compound angle formula. So we know that from the compound angle formula, we should be knowing that when you have sine a plus b, this is the same as writing it as sine a, okay, cos b plus cos a sine b. This is what we do have. This is from this rule, that is the compound angle rule. We also know the one for the cos. We shall look at the one for the cos, but let's focus on this one here for the sine. So therefore, when you do have when we now have a sine x plus small change in x, this will be the same as when you do a substitution for a and b respectively. We shall have sine, okay, our a is x, so it should be sine x, cos b, our b is small change in x, okay, then plus cos x, then sine small change in x. This is what we have. So we substitute in the derivative formula here. So this will be equivalent to, cos, we have the limit as the small change in x tends to 0. Then we substitute for sine x plus small change in x, so we shall put this, okay, we shall substitute it with this, so we shall have sine x cos small change in x plus cos x sine small change in x minus the sine x. Please do not forget this other sine x. Then all this we are dividing through by a small change in x. But remember, we are dealing with small values of x, meaning we are using the approximation. So from small approximations, angle approximations, from small angle approximations, we should be knowing that when you have sine x, sine theta, this sine theta tends towards theta. That is for small angles. Then what happens to the cos theta? For the cos theta will tend towards, or will be approximated to 1 minus a half theta squared. We are generating this from the knowledge of small angle approximations. So what do we have here? We do the same thing, but now we have x. Okay, we have now small changes, which is small change in x. So here we mean that sine small change in x, okay, our sine small change in x will tend towards to small change of x. And for cos small change in x, this one will be tending towards to 1 minus a half. Our theta is small change in x, but it is now squared. So you do a substitution here again. We do carry on a substitutions for these small changes in x, and then for 1 minus a half small change in x squared. So we continue. So we say the limit as small change in x tends towards 0. Our sine x remains, so we shall have sine x into cos small change in x. We substitute it with this, so we shall have 1 minus a half small change in x squared. Please don't forget the squared plus cos. Our cos x remains. We have our cos x. Sine small change in x, this one will be small times small change in x minus the sine of what? Our sine of x. All this, please don't forget that we are dividing through by a small change in x. So we open up our brackets here. So we will be having, when we open up our brackets, we shall have limit a small change in x tends towards 0. When you open sine x times 1, we shall have sine x minus a half small change in x squared sine x, okay, plus small change in x cos x, okay, minus our sine x, and all this will be out of our small change in x. So we pull out the like items. You realize that we have sine x minus sine x, which will be 1, which will be 0, which will move down to 0. Then we will be remaining with these small changes. These small changes can be reduced down. So this will be 1. Then this one will reduce down to 1 small change in x. So therefore, we shall be remaining with the limit as small change in x tends towards 0. So we shall have minus a half small change in x sine x, okay, plus cos x. Okay, remember we've tried to reduce it down. So therefore, we know that our small change in x tends towards 0. And if the small change of x tends towards 0, it means that our negative a half small change in x sine x will tend towards what? Will be 0. Because this small change will be 0, it will multiply through everything, will be 0. So therefore, we shall remain with dy dx, we shall be remaining with what? With cos of x. So this will be our final derivative. So when you differentiate your sine x, you'll be able to get your what? We shall be able to get our cos x. So this will be your final result using our first principles to carry on that differentiation. Okay, so that's how we try to use our first principles. But what we should pay close attention to are these the compound, okay, this compound angle formula, and also the small angle changes here. These ones are key to helping us get to that given point. Now, moving on, we need to look out for what happens to when you move on to when you're using the sine. So when you're using the sine, we shall be having so take an example. If you have your y, if we have our y being equal to cos x, and we are told to differentiate that. So still we are using the same procedures. We know that dy dx will give us, we have the limit, a small change in x tends towards 0, a small change in y out of small change in x. Okay, so this will give us, we do the substitution. So we shall have the limit, a small change in x tends towards 0. So here we have cos, we have our cos x plus small change in x, okay, minus our cos x. All this is out of the small change in x. Still we bring back our compound angle formula. So from the compound angle formula, we know that when we have cos A plus B, cos A plus B, this is the same as cos A, okay, cos B minus sine A sine B. This is also bringing us to this. So therefore, if you have this, if you have cos x plus small change in x, this will be equal to, we do a substitution knowing that our A is x, okay, your A is x, and your B is small change in x. That's what you have. So do the substitution here. We shall be having, we shall have our cos A, which is x, okay, cos small change in x, minus sine x, sine small change in what? Small change in x. Okay, then we do the substitution again. We do our substitution in this equation. So we shall be having our limit, a small change in x tends towards 0. Okay, so we do a substitution, we replace it with this, which is cos x, cos small change in x, minus sine x, sine small change in x, minus cos. All this is out of x, cos x, out of the small change in x. Okay, so still we bring back our approximation rule. So from approximation, okay, from our small angle approximations, the small values of small angle approximation, we know that when you have your sine theta, this one tends towards the theta, and then the cos theta, this one tends towards 1 minus a half theta squared. Okay, so but our theta here is being taken as the small change in x. So meaning our sine small change in x will tend towards what? Small change in x, and our cos small change in x will tend towards 1 minus a half small change in x squared. That's what we have. So same thing, do the substitution. We do the substitution again. So we shall have the limit, a small change in x tends towards 0. Okay, limit a small change in x tends towards 0. So we do a substitution here. So cos x will remain as cos. So we shall have cos x into the cos small change in x will be 1 minus a half small change in x squared. Please don't forget the squared. Then minus sine x, which is our sine x, which will remain, times sine small change in x. Our small change in x will remain that, and also minus our cos x. All this is out of the small change in our small change in x. Okay, so we open up the brackets. We open up our brackets, so we shall have limit as small change in x tends towards 0. So we have cos x minus a half small change in x squared, still cos x, minus small change in x sine x minus cos x. All this is out of small change in x. Okay, so literally you see that what is trying to bring us to the point that we need are these small change angles and then the compound angle formulates. That's what we need to have in mind as we carry on these solutions. So we know that our cos x will go with cos x. Then we know that this small change will reduce down. This will be 1, and also this will reduce to 1. So we will be remaining with the limit as small change in x tends towards 0. So we shall have negative a half small change in x cos x minus sine x. Okay, but we know that we should be knowing that our small change of x tends towards 0, so meaning this a half, or rather negative a half small change in x cos x will also tend towards 0, because when you small change x is 0, that means when you multiply through it will be 0. So therefore we shall remain with dy dx of cos x being equal to, we shall be remaining with negative sine x. So this will be our final result when you differentiate your cos x. Okay, so that is how you try to work through. Still, I still emphasize this, that take note of this the compound angle formula. It's very key. It's the one that is giving us most of the work, and also these small changes in angles. Okay, and these ones are usually they're derived from the right angle triangle. When you try to get the area of the triangle and areas of the sectors, this is what we will be able to come out to. Okay, so I also say that all this is going to help us when you're carrying on the differentiation of the sine and then the cosine. The chain rule comes in. Okay, the chain rule is very key when you're trying to solve this, and the chain rule is literally the repeated multiplication. You're multiplying something. So the chain rule says that when you're having dx dy, when you to get dx dy, we get dy du times du dx, and this is the chain rule. This is how it goes and how it is supposed to be stated out. So when you do have this is the one that will help us also to work through in our differentiation throughout. We are going to look at examples and we see how we can be able to apply it in our working. So let's take an example. Let's look at some examples. Let's look at some examples. So we have examples. I'm going to work out about 3 examples and then we shall be able to work through. So we are told to differentiate with respect to x. So 1, we have y being equal to sine 2x. Then 2, let me write all of them. We have y equals to 4 cos 3x. Then 3, we have y being equal to sine ax plus b. A and b are constants. Okay, a and b are constants. A and b are constants. And we also have y being equal to cos x squared plus pi, x squared plus pi. Okay, we'll keep adding on more other work from there. So that's what we do have. Okay, so to start with, we have Roman 1. We have our y being equals to sine 2x. How are we carrying on our differentiation here? Now, when we are differentiating here, we are going to use the other result that we got for differentiating the cosine and the sine respectively, and also the chain rule. And the chain rule is going to guide us fully. We know that from the chain rule, dy dx is equal to dy du times du dx. So how does the u come about? So we do a let. So we say let our y be equal to sine u. We are introducing in our u. So what will this u be? Our u will be this term 2x. Okay, so what does this mean? You're going to differentiate this one separately and also this other one separately. Okay, so what will dy du will be equal to, remember when we differentiate, when you differentiate sine, you get cos. And when you differentiate cos, you get negative sine. That is now what we need to have. So when you differentiate this, will be cos u. That's what we will get. Okay. Then when you differentiate this, the u with rest the x will be, when you remember our rule for differentiation, you get the power, you bring it down, multiply it by what is there, and then reduce the power down. So we shall remain with, this will remain with 2, and you differentiate that. Okay, so we now combine the two. Combining means that dy dx will be equal to dy du times du dx. So we are multiplying. So this is the same as cos u times the 2. Okay, so this will be equivalent to 2 cos u. But remember, your u is equal to 2x. So you substitute, you do the substitution. So this will be equal to 2 cos 2x. So this will be your differentiation of that given term, and this will be your answer for that. Okay, so we've known the other differentiation of the sine and the cosine. Then once you know that, then we just carry on the substitution. Let's do the second one as well. So still the second one here, we have our y as 4 cos 3x. Okay, cos 3x. So once you do have that, what do? We still do the same thing. We do the letting. So we shall say let our y be equal to cos u. Okay, that means that your u is equal to the 3x. Please, this one is a constant, so this one you maintain it as it is, don't tamper with it. Okay, so therefore we differentiate this. So dy du will be equal, when you differentiate cos, you get, we said we get negative sine, then the u. Okay, then when you differentiate this, so we shall have then du dx will be equal to, this will be 3. Okay, so finally we shall have this negative, we now multiply, that is dy dx. Okay, dy dx will be, please maintain this 4. Actually the 4 should move with it, the 4 should remain, don't leave out the 4. So this will be negative 4. Okay, the 4 remains, don't leave it out. So this will be, dy dx will be negative 4 sine u. Okay, negative 4 sine u times the 3. So this will be equal to, this will be 3 times the negative 4, this will be negative 12 sine u. Please finally make sure you do the substitution. We know that our u is equal to 3x. Our u is 3x. So therefore, the dy dx will be equal to negative 12 sine 3x. Okay? Sine 3x. That's what we do have. So keep in mind, like when you have this constant at the beginning, that one should remain, we should keep moving on. You keep moving on with it. You don't change it out when you're working through. Okay, I think you can now even do the other ones, but let's still work together through. Let's work together. So the next one was saying, we have y being equal to sine ax plus b. That's what we have. So still we say let our y be equal to sine u, and now here our u is this, okay, that entire equation, which will be ax plus b. That's what you have. So dy du will be, when you differentiate sine, we get the cos of u. Then when you have du dx, this will be, okay, these are constants, okay, so when you differentiate this, we shall remain with what? With a. When you differentiate, because that means x is the one which is a variable. So this x, this constant a and b, these ones are like the way you see 1 and 2. So when you differentiate 1, you have 0. Okay, so when you combine them, we shall have dy dx being equal to, we multiply the 2, which will be cos u times the a. So this will be equal to a cos u. But remember, u is equal to ax plus b. Okay, so we do a substitution. So this will be a, this will be cos, so we should remain with our cos. U is ax plus b. Okay, our u is ax plus b. So at the end of it all, we will remain with something like that. Okay, so literally we will, you keep on practicing more and more, and then you'll be able to see that that is what you'll be able to get. Okay, now I would leave you, I'll lead you to work out this other one. I'll leave you with this one here to try to work through this one here. You'll be able to work out using the same methods to be able to work out with that. Then let me work out one more example. What if we are told to differentiate and our y is equal to, let's try to differentiate this. If we do have our x, let's try to differentiate with respect to x now. If we are differentiating with respect to x now, so if we have our x, okay, being equal to sine squared theta, this is what and we need to differentiate this. What do we do? Now this time around, you see that we are now differentiating with respect to something else different from what we had the other side. So meaning here we are going to differentiate dx the theta. Okay, dx the theta, that's what we are going to do. Okay, so if you're to differentiate now dx the theta, we shall have dx du times du the theta. Okay, that's what we are now going to have. So meaning, still this time around, the other time we're letting y, so this time around you're letting x. So this time we are going to say let our x be equal to what? To u. Okay, squared. Okay. Now, maybe something else we should be knowing, that this one here, that when you have sine squared theta, it's the same as sine theta squared. These ones are the same things. So that's why we are saying we are now letting our x to be equal to u squared. So this, our u now, our u is now what? Our u here is now sine what? Sine theta. That's what we will have as our u. Okay? I repeat, we said our x is equal to sine. This is what we're supposed to, but when you put it in a simpler form, we have sine theta squared is the same as sine squared theta. These are the same things. Okay? So you simplify it in that form. So this time around, we are saying that instead of saying y being equal to sine something, but this time we are instead using our x as the u squared. And our u is now what? Is sine theta. So you differentiate these two here. So dx du will be, when you differentiate this one, will be 2u. Okay? Then for du, the theta, remember when you're differentiating sine, you get what? You get cos theta. That's what you get. So therefore you do the substitution. So our dx d theta, okay, will be equal to dx du, which we've got, which is 2u, times du d theta, which is cos theta. That's what you have. So this will be equal to, okay, this will be equal to, remember your u is sine theta. So this will be equal to 2u is sine theta, which is sine theta cos theta. That's what you have. Okay? That's what we do have. So this will be dx d theta. Now you can leave it like this, or you can put it in its simplest form, knowing that when you have 2 sine theta cos theta, it is the same as sine 2 theta. Okay? But if you leave it here, it is also well. Okay? If you leave it at that point, it is also fine. But this will be your final point. So be dynamic when you're trying to solve through these equations here. Maybe let me work out one more. Let me work out one more related to this one here. If we do have our y, let's now use y. If we have our y being equal to cos cubed 4 theta, okay, and we are supposed to differentiate. I said we can put this one in the simplest form first. So what will the simplest form be? This is the same as y being equals to cos 4 theta cubed. 4 theta cubed. So when you have 4 theta cubed, this will be, it will make it easier for us to carry on that expansion. Okay, you make it easier to expand that given part when you have. So now we are letting, we say let our y be equal to, so we take this one to be u cubed. Okay, this entire cos 4 theta will be u. And knowing that our u is equal to what? Is equal to cos 4 theta. That is your u. Okay, that's your u. So therefore we shall say dy du, okay, dy du will be 3u squared when you differentiate this one here. Okay, then when you differentiate this other one, when you differentiate du the theta, okay, now remember this one here, you're going to go back to the other first method that we used. Remember how we differentiated the other first ones when we were differentiating these ones here. Actually, this is what you're going to go back to, but when you differentiate that, you'll be able to come up with 4 sine 4 theta. Try to do the, remember where we are saying we are letting this, we are letting y to be this, then the other one, and then you carry on that differentiation. You will still come back to this given part. So therefore we shall now have our final part where we say our dy, I think it's dy d theta will be equal to, so our dy d theta, we shall be able to have negative, we shall have negative 4 sine 4 theta times 3u squared. Okay, so this will be equal to, when you bring this at this side, we shall have negative 12 u sine 4 theta. Okay, sine 4, actually it's negative u squared. Okay, negative u squared. So finally, when you substitute in, when you we do our final substitution, when you do your final substitution, where we know that our u is the other, so we shall have 12 u easy, our u easy, when you check through your u easy cos 4 theta, so which will be 12 cos 4 theta squared sine 4 theta. Okay, so this will be your final result. So I said you may simplify it the simplest form possible, or you can also leave it at this as well. Okay, remember, someone can also write it as, actually remember this 12 is negative, you can also write it as negative 12 cos squared 4 theta sine 4 theta as well. Okay, so I really want us to try to do more practice before our next video, before you go through the next video, because our next video is going to help us connect right from this point, where we shall do, or rather carry on more and more other differentiation as far as this work is concerned. Thank you so much for listening. Please keep subscribing and keep watching these videos over and over. If you do not understand, please leave a comment and we'll be able to answer your responses in the corresponding videos. I thank you very much and God bless you.